As great as you are. All right. Yeah, that's one thing. Your hand on the fix of God. All right. It's on the right side of the board. That's beautiful. Okay, let's get going now. All right, Calculus 2, we are back. So on that last video, I was going to try to do both the trig integrals and the trig substitution integrals, and took a while on the regular trig integrals, so we didn't quite get there. So on this video, let's work through these trig substitution integrals. So this is section 8.4, and as I was kind of saying at the end of that last video, you'll see that this is actually a short section, but definitely some stuff to not only work on, but sort of pay attention to. So let me show you again. I'll start with, let me just write up one of the intervals we're going to do, and let's talk about kind of what works, what doesn't, how it's similar, different from what we've seen before, etc. Okay, which one? So we'll look at number 3. Number 3 is the integral 1 divided by. I'm actually going to write it. I'm going to write it a different way than they read it off in the. So this is going to be square root of 16 minus x squared dx. I'm actually going to change this problem slightly from the book. In the book, it's to the 3/2 power, so this is really cubed. But to sort of make my point here, let me just take off the cube for now. So we want to do the integral of 1 over square root of 16 minus x squared. Now, first thing, so again, I want you to look at that, pretend you don't know what section you're in, you don't know that there's some certain method you're supposed to do. Based off of what we know so far and what you've seen so far, what does this look like? What method does this look like you can use with it? What should we check for? What problems does this look like? We have seen problems a little bit like this before with the square root on the bottom and some expression in here. Usually the expression in here just had an x instead of an x squared. So the question is, does that really make that much of a difference, right? So it shouldn't. So then kind of part of my question is, how is this the same and how is this different from problems you've seen before? So it's the same because we have seen square root on the bottom and expression in there. It's a little different because we haven't seen a squared so far, but there's nothing kind of telling that should make it any different, right? So let's say we did try to approach this. Well, what else is different maybe? And you may see it and may not. The other problems that we've seen, they tended to have, well, sometimes they had a 1 up here, but sometimes they would have like an x term up here, right? So let's see, this is a little different, but it doesn't seem that much different from problems we've done before. So let's try some of the methods we've done before. So we first did integration by substitution, and that's the first thing you want to check. So can you do this by substitution? And I actually want to give you guys a second to check that. So pause on your side, I'll pause on my side. See if you can do this by substitution. All right. So what did you find with substitution? Good. This is going to be the first huge difference. So the thing is, this looks like, honestly, quite like a problem that maybe we could do with substitution. Substitution would have to be u equals x 16 minus x squared. But then, so if u is that, then your du is going to be negative 2x dx. And we don't have a 2x anywhere here. We can't even sort of massage it out of there using some sort of algebra. So this is the first huge difference in this problem compared to some of the problems we saw when we were doing, especially when we were doing substitution, is it's missing piece you need from the derivative that you need in substitution. It's missing that piece. Again, previously, so a lot of times you didn't have the squared, so you could get away with that because EU just ended up being dx, so you didn't need something up top. But otherwise, when you did have an x squared or some bigger power there, then you had something like this up top, and we don't have that. Good. All right, so can't use substitution. Now the second legitimate thing to think about is, could we use integration by parts? But notice that for integration by parts, I need two functions multiplied together, or, technically when you divide two functions, that also works because it's just 1 over second function. But we don't even have that. So notice that we don't even have that. So we are again sort of stuck in, so we're stuck with a function that actually doesn't work by integration by substitution or integration by parts. Notice also this isn't a trig ratio. So I'm title of this section is trigs, integrals by trig substitution, right? So you would expect these to be trig ratios, but they're not. So what in the world do we do with this? And why do I call it trig substitution? So what we're going to look at today only works specifically with problems that have a square root with terms in here. Notice that x squared is obviously squared, but so is the 16. So with a term in here that is essentially a sum or a difference of two things squared. So that's the one thing I'll emphasize about what we're going to learn today and why it's not going to take long, is it is a very specific type of problem. It happens to be problems that we can't handle with substitution or integration by parts. And the specific form has to be that you have a square root, and usually it's 1 over. It's not always. Usually it's on the bottom of the fraction, but it's not always. But specifically a square root with something squared here plus or minus something squared here. If you have that set up, though, so the book kind of splits this into like 3 sort of styles of problem. What I'm going to show you guys is all the problems we're going to see today are really just one type of problem. It's putting together the picture and kind of recognizing the pieces that's gonna change slightly between these problems, but they're really just one type of problem. So if you have this form, then I want you to think about this piece that I'm highlighting on the bottom, square root of 16 minus x squared. And this may not ring a bell for you, but does that form look like anything to you that you've seen in mathematics before? And again, maybe it doesn't, but some of you might be saying that it kind of looks like distance formula, or maybe kind of looks like Pythagorean theorem, right? Maybe it looks like this calculation came from Pythagorean theorem because we're taking the square root of one thing squared, in this case minus another thing squared. Now, even if you didn't see that and you see that now, so I say it looks like Pythagorean theorem, well, kind of whoop-de-doo, what does that do for us? Here's the fun thing about this. What I'm going to do is I'm going to build a triangle that mimics the calculation that basically uses Pythagorean theorem. Give me this calculation that I'm showing here. And once I've built that triangle, see, we're going to go back to pre-cal and use our knowledge of trig ratios to make a substitution in this problem. So this problem as it is can't do the thing. We cannot take the integral of this. So this is why they call this sections trig substitutions. Once we build the right triangle that kind of corresponds to this square root part, we label it. You're going to find that you're going to be able to make a substitution on this problem out of that right triangle that actually changes this integral into a whole nother integral that we're easily going to be able to do. Or at least, you could at least do by substitution, I think. So this kind of looks like Pythagorean theorem. Which means this we can imagine as if it came from a right triangle. So I'm going to draw a right triangle. And let's say I'm going to put theta here. Now, if this came from some calculation that I got by running Pythagorean theorem, that means that if you think about it, that means that this 16 have to have come from the hypotenuse because we're subtracting one of the legs squared. Literally, you think about it, one way to think about this is this was the result of 16 equals x squared plus another thing squared. I don't know what the other thing is, so we'll call it a. And I'm subtracting x squared from both sides. And then I'm taking the square roots so that I could figure out the length of leg A. So, and let's say, so the A is a leg, so let's say I put A here. Then that means that this side is my other leg, so this is an X. So X is, I need to put here what's being squared to make X squared, and then you need to put here what's being squared to make the 16, and what squared gives you 16? That's a 4. Give me a second too there's a reason they do certain substitutions in this section, but I want to see if we can get away with doing. Pretty sure we can still get away with doing it this way. Let's go. Yeah, we can. Okay. Yeah. I just want to make sure. So. Good. Now, the first thing you may be thinking is, hold on, like where in the hell does this come from? Like why in the world would you even think about creating this? And I do want to admit that so this little substitution scheme, where does this come from? This is somebody who's being ultra abstract and connective with connecting the thing they're seeing with some distant part of mathematics that doesn't seem to relate, but actually does, or at least you can actually make the connection. So I'm not saying that there's nothing about this right triangle that would that would not be your first thought coming out of an integral, that you need a right triangle to do a substitution right here, right? Completely out of left field. So I will completely admit that. But we're going to do this probably 3 times just to get you guys used to it. But again, the key is you'll see it does work. So surprisingly, it does work. And the tip off for this really is this square root of 16 minus x squared. This looks like the results, like I said, if you plugged in a, x, and 4 into Pythagorean theorem and then solved for a. Just looks like the type of result that you will get. So you have seen those results before. You've seen them in college algebra. You saw them in pre-cal, probably saw them in a geometry class way back when. So it's like you've seen that type of result in that pattern. And that really is, whoever figured this substitution out, that really is what happened. I mean, they just looked at it and said, oh, this kind of looks like this. It really was this trial and error. Let me build the right triangle that comes from and see if in any way that helps us do this integral. That is literally where this comes from. So again, it does sort of come out of left field, but the good thing about this, or the thing I want to encourage you on it is just a trial and error thing. And we basically are doing the same thing that whoever figured this out is doing. See it, say, looks like it came from a right triangle. You build the right triangle and you're not even sure how this is going to go forward, but you're just kind of saying, let me see if I can use this right triangle, change this, what do you call it? To change this integral into something I can work with. Let's just see what works from it. So now in terms of this integral, again, this integral is in terms of x. This a, not only do I not know the value of a, it has nothing to do with my integral here. So I'm not going to worry about that. But notice that once I've labeled the right triangle this way, the two things that I do know here, x and 4, in terms of this integral, x over 4 is a specific trig ratio. So the next thing you're going to do is, like I said, you got to figure out something from this right triangle now that you can use to kind of transform your integral. And notice that x over 4, opposite over hypotenuse, is a trig ratio. What trig ratio is that? Good. So from this right triangle, I can say that sine of theta equals x over 4. And that tells me a couple other things. So notice that once I have this, then I can solve for 1, you can solve this for x. So x is going to equal what? X equals 4 sine theta. And so hopefully, so what I'm doing here is I'm trying to, so once I read that sine of theta is x over 4, I'm then going to use this to try to create the things that I would need to plug in here, the things that I would need to substitute for. So in this integral, I need to substitute for x and dx. And we've done that for all of our, kind of substitute or integral schemes so far. So remember, with the integration by substitution, you would figure out a u and then you'd figure out the du, right? And you'd plug those in, and then at the end you'd re-substitute things in. And when you did integration by parts also, you started with a u dv and you figured out the other parts of those du and v, and then you'd plug things in, right? So we're not doing really anything different here. It is a substitution methodology or kind of strategy. It's just the substitution is different than that's a different way to get at a substitution than we've done for the other two methods. So sine of theta equals x over 4 automatically tells you that x equals 4 sine of theta. And once I know x, I can figure out dx. So we don't even have to pause. Just take a minute there. What's your dx going to be? Your dx is going to be 4 times cosine of theta and d theta. So now again, every method, every strategy we've done with substitution, once you've kind of figured out what your pieces are, you substitute those in. So let's substitute those in. End up with 1 over the square root of 16 minus 4 sine theta squared. And my dx is 4 cosine theta d theta. And notice first, before we start simplifying stuff, notice that now everything in this integral is in terms of theta and d theta. So once I start working stuff out, both algebraically and, with some trig identities, this is going to be an integral in terms of theta. So I'm going to integrate it in terms of theta, which means that when I get back, when I get to the end of this, I'm then going to have to replace theta with what it is in terms of x, right? So that's another thing we're going to have to figure out from here. What is theta in terms of x? But anyways, so let's keep moving on this. So what do you see that can be done here? What do you have to do really? So the 4 sine squared theta, I got to square that. So 1 over, actually, so what I'm going to do is it's 1 times 4 cosine theta d theta. So I'm just going to put that up top. So it's 4 cosine theta up top, theta. Then we're going to have the square root of 16 minus 16 sine squared theta. . Notice that there's some interesting things going on here. So 16 times 16 minus sine theta. So I can factor out a 16. That leaves me with 1 minus sine squared theta. And hearkening back to our last lecture, but again, hopefully it just jumps into your head. 1 minus sine squared theta. What does that equal? The Pythagorean identity says that's cosine squared theta. This is the integral of 4 cosine theta over the square roots of 16 cosine squared theta. And what is the square root of 16 cosine squared theta? Well, hopefully, as you're going to, I mean, you're giving me the answers, but hopefully you're being surprised. I don't know. So hopefully you're in a state of surprise. Because what I'm saying is, again, this, we couldn't do anything with this. But by doing this weird, odd substitution that we just kind of naturally find from the right triangle that corresponds to the square root, suddenly now we're getting a lot of simplifying that we can do. We're getting a lot of work, and it's really trying to kind of changing this into something completely different. The square root of 16 cosine squared is 4 cosine theta. So we have 4 cosine theta up top, 4 cosine theta on the bottom, theta. Those all cancel each other out. So this ends up just becoming the integral of d theta. What is the integral of d theta? 1 theta. That's theta plus a c. Now, what is theta? So by the end of this problem, we gotta give our answer in terms of x, because our original integral we were trying to integrate in terms of x. What is our answer in terms of x here? Well, going back to this, then the question is, what do you do to isolate theta? How would you solve for theta here? To solve for theta, I mean, basically theta is just the sine inverse. So sine inverse reverses this, or kind of cancels out the sine. So sine inverse of x over 4 would have to equal theta. So my answer is sine inverse of x over 4 plus c. That is the integral 1 over square root of 16 minus x squared. So this is correct, but I think there's a different way that they're coded, so that they're undoing this part. If we have to worry about at least be equivalent. This is good. So that's our answer there. But notice that taking the integral of that gives you something wildly different actually in terms of functions. So we've seen taking the integrals of polynomials gives you polynomials, and taking the integrals of what do you call it, exponentials gives you exponentials. This is one among, this is not the only, but one among, some types of integrals and functions. You'll see where you do the integral, you gotta kind of get something wildly different from it. But this play of creating a right triangle out of the square root parts and then using that to make your substitutions, that's actually the thing in this section, or that's the crux of this section. That is what we're going to be doing. So, like I said, we'll do, we just kind of need to run this through a couple times. We'll do one or maybe two more of these, and that's it. Let's do. Yes, let's look at two more. So the first one, let's look at 9. Want the integral. X cubed here, and then the square root of x squared minus 25. Yes. So now again, notice that, well, this one, again, you want to think substitution. And again, where this fails with substitution, if this would have to be my substitution, u equals x squared minus 25, but then my du is 2x. We have much more than 2x out of here. We have much higher power. So kind of on 3, we basically didn't have any x's. We sort of had x to the 0 power where we needed x's. Here we have way too many of them. We have x to the 3rd power instead of x to the 1st power. So again, this is not going to work by substitution. This one then technically you do by integration by parts. Well, can you? Yeah, I mean, it's going to take you several iterations, but you can get there. However, it ends up, trig substitution is much easier. So again, once you see the square root of a square plus or minus a squared, that's going to be your hint that this is, trig substitution is not only a play for this, but it's your best play, even if there is another way to go about it. So again, what we're going to do is we're going to build a right triangle from the square root of x squared minus 25 from the radicand part. So right triangle, sure, angle anywhere, but let's say this is where my angle is. Then looking at this, again, you want to imagine basically sort of where this would come from Pythagorean theorem. sort of with that in mind, then where is your X and your 5? Where are the pieces here? So hopefully you can maybe see this again. Because we have subtraction, that means that whatever you're subtracting had to be a leg squared, and whatever you're subtracting from had to be your hypotenuse squared. So that means that this was an X, then maybe this is a 5. There. Oh. So this leg, so the kicker with this leg is it could be either one of these. And give me a second there. So I think it actually doesn't matter. I think we get equivalent solutions either way, but let me also work that in my head and debate it. I think it's gonna be equivalent either way. So let's say we put the 5 there. And again, this comes from doing x squared, hypotenuse squared, minus this leg squared, taking the square root, which then is the solution for this part here. That's the solution for that leg, which would make this leg basically is literally our square root of x squared minus 25. But again, once I have this, I can read off a trig ratio involving the x and 5, and then do the same thing I did over here. Solve for x, solve for dx. Also go ahead and go back and solve for theta. So then using the x and the 5 here, what trig ratio could we define what we have in this I call it this right triangle? One of the ways you could say this is 5 over x. That's sine of theta, right? We usually want our x to be on top so we can solve for it. So you might read this as x over 5. So 5 over x is sine theta. What is x over 5? Which trig ratio is that? That's the reciprocal, the cosecant. So I would say here that cosecant of theta equals x over 5, which means that x equals 5 cosecant theta. If that's x, what is dx? What is the derivative of 5 cosecant theta? Good, and hopefully you remember that would end up being -5, would be cosecant theta, and then you tack on a cotangent theta. This also tells me that theta is the inverse cosecant of x over 5. So all of this is just a little bit of algebra, a little bit of solving, but also this is just pre-cal. This is all of kind of the ideas and concepts you have from pre-cal, especially the trig ratios, and when you're looking at it from a right triangle perspective, all kind of wrapped up into one. But once I have that, I can start plugging these things in and then solving for what I have there. So what I'd like you guys to do is I'd like you to take these substitutions and actually plug them in and simplify this as much as possible. And if you get there and you realize you can take the integral, you know how to take the integral, then do it from there. But at the least, what I want you to do is plug in for x, plug in for dx, then see how far you can simplify that. So go ahead and pause on your side. I'll pause on my side and see what you get out of that. All right. So starting to place this stuff in. So not only are we getting 5 cosecant theta here, but we're also getting it out here. So the integral, we're gonna have 5 cosecant theta cubed. Inside, we're gonna have the square root of 5. Letter. Secant squared theta, or sorry, this thing cubed, this thing squared, minus 25. And all of this also times -5 cosecant cotangent theta. So I'm just gonna sort of put that down here because we don't have to write it there. This was theta somewhere at the end here. Theta. All right, that's my dx. All right. Then, oh, I see why they went with secant. So the book went with secant instead of cosecant, but we can play that. We can do the same thing we did yesterday. So actually, this is a good. It's actually not only a good accident, but so one of the things I do want to emphasize with these problems is, again, the book says to use certain call it substitutions, but honestly, you should use the substitution that comes naturally out of the right triangle that you build. So basically, I'm trying to teach you to do this. So sometimes in a section like this, in a textbook, it's like in order to have some nice convenient ways for students to look at it and work through it, we sort of invent a technique or say, here, use this, here, use this, when in general, like in reality, you don't need to. So what I'm trying to say with all of these problems, as long as you build the right triangle, the substitution that you find from the right triangle, whether it matches the one the book is saying, for that problem, is whichever substitution you use is gonna be correct, and it's gonna get you correct answer. So I'm basically trying to teach you guys again to be problem solvers and thinkers through these problems, because in reality, that's what you can do with these problems. You don't have to use in this case, and especially in this section, the very specific substitutions they mention. You can use any correct substitution that comes out of your right triangle. And one of the things that does is it makes these problems a lot easier because you're not thinking, oh, this problem, it's this problem and it looks this way, so what's the substitution I should use every single time. So basically I'm saying there's no difference in any of these problems. Every single time you build the right triangle, find the substitution from the right triangle and go. And I promise you the integral works. So that way you just have one approach at all these problems, and you're also depending on yourself to draw the triangle and really create the substitution, really think your way through the problem, rather than trying to just memorize something. It would be hard to memorize anyways. So hopefully that kind of makes sense. So even as I'm doing this problem, I'm realizing kind of, they had a certain substitution in the book for this problem, and what I'm doing is still going to work just as well, right? So anyways, all right, so first of all, it looks like, notice that we now are gonna have these cosecant is gonna get multiplied into here. And we're gonna be getting some work out of here as well. It's looking like, so I'm actually not sure completely yet, but it's looking like this problem is gonna look a lot like the problems we worked on with the last lecture, where you're gonna have cosecant raised to a power, and I assume if it's cosecant, then hopefully gonna have cotangent raised to a power somewhere there, right? So in the previous lecture, we kind of, the second half of the problems we looked at had secant and tangent integrals of products of secant and tangent to different powers. So all I'm saying is I'm sort of looking at this in my mind. I'm like, oh, this might end up like those problems, but it'll be cosecant and cotangent. But like I showed you guys on that lecture when we were looking at the Pythagorean identities, cosecant and cotangent are connected by the Pythagorean identity. They're also connected by derivatives. So what I'm saying is I'm anticipating once I simplify all this, I basically am going to be solving this problem like problems we solved yesterday on the previous lecture. That I'm going to be using one of those schemes, which is why this section is after that section. Anyways, so let's start simplifying some things. 5 cosecant, we got 5 cosecant cubed, so that's going to end up being 125 cosecant cubed theta. Let me just put that in parentheses. You don't need parentheses, and then we're going to have square root, and we're going to have 25 cosecant squared theta minus 1. Sorry, minus 25. I am fast forwarding ahead in my mind. And then still times -5. I'm still writing that backwards. -5 cosecant theta cotangent theta d theta. Sure, that's good. The d theta at the end. Notice I'm gonna get to multiply. My this through to here. We also got to start simplifying what's going on here. So I'm going to factor out a 25. So I'm going to kind of do both in one step. Multiply this through to here, then do my factoring there. So the integral, then I'm going to end up with -625. Okay, yes. This is going to be cosecant 4th power theta now, the cotangent theta. And then the square root of 25 times 1, 25 times cosecant squared theta minus 1. Good. So then again, hopefully this has given you a lot of flashback from our problems yesterday. So you're now going to be using a lot of the same trig identities, and we're even, it looks like, going to be using the same methodology to solve this. So the cosecant squared theta minus 1, hopefully that rings a bell with your Pythagorean identities. What is that going to equal? So that should just be cotangent squared. Hold on a minute. Yeah, let me make sure I got that right. Sine squared plus cosine squared and secant. So we're dividing by sine squared. So 1 plus, yeah, so Pythagorean identity says 1 plus cotangent squared equals cosecant squared. So cosecant squared minus 1 is cotangent squared. So I'm going to replace that. It's now going to be the square root of, it's forwarding in my head, 25 cotangent squared theta. All this with a d theta on the end. I forgot that last time. And what is the square root of 25 cotangent squared? That's going to be 5 cotangent. So, so just step by step. Minus 625. Cosecant to the 4th, theta, tangent theta, times 5 cotangent theta, theta. Now notice I can multiply that farther in. So we end up with, bring this all the way over here. In grand total, I end up with, so 5 times, that's going to be 3125. So the integral of -3125 cosecant to the 4th theta cotangent squared theta d theta. So again, this weirdly wild, strange looking integral to begin with a square root and a cubed function ends up being something like this. And let me see how much that goes. Yay. Now, again, hopefully you see this and you're like, oh crap, that's actually looks exactly like the type of problems that we solved on yesterday on the last lecture. And indeed it is. So again, this is why I wanted to include this on that lecture. But indeed it is. We have cosecant raised to a power, we have cotangent raised to a power, just like the back half of that lecture, we saw secant raised to a power and cotangent raised to a power. So that means you want to take the same strategy, same approach. So basically, either my substitution is, I'm gonna start by, I want to get to substitution with this, and I'm gonna start then by either making my substitution u is cosecant or u is cotangent. And the way you figure out which one it is figure out your DUs for those and just figure out which one of those is basically is easier, or just you can pull out as a factor from what you already have. So what I mean by this is, so let's assume u is cosecant theta. If u is cosecant theta, what's du going to be? Give you a second for that. So du is going to be what? Cosecant theta, cotangent theta. And I do have a cosecant and I do have a cotangent, but it also leave me with an odd number of those. So again, when we're using substitution, the idea is basically whatever my substitution is, sort of the other part should just be everything, you should be using the rest of it as the du. So this is, maybe it would work with a lot of algebra, but it's not the best substitution in this case. Let's look at it the other way. So what about if u is cotangent theta? If u is cotangent theta, what's my du? Good. My du is actually negative cosecant squared. We'll use up that negative we have. Negative cosecant squared theta. Theta. And notice that I can kind of factor off of this cosecant to the fourth. And so we'll do that, and you'll notice this will look a lot like several of the problems we looked at yesterday. And once you see that, you'll know kind of the strategy forward. So again, I want you to notice that the other thing I want you to notice, just a meta thing to notice, is we didn't do any problems with cosecant and cotangent yesterday. However, we are going to be able to work through this problem, and you're going to be able to work through a problem like this, because you're recognizing that the methodology, you're recognizing from what you saw yesterday, even though it was secant and cotangent and tangent, that the methodology is the same, that it's going to work out roughly the same. So again, just sort of notice that when you're doing these homework exercises, you don't need to have seen everything in order to be able to do a problem. And honestly, that's when I'm teaching you guys this on these lectures, I am not trying to teach you every problem in the homework. I'm trying to teach you the core problems, but really ideas and concepts necessary, strategies, critical thinking necessary, so that if you see a problem you haven't seen before, you still can tackle it, because you'll recognize that it's similar to another problem. You'll see the differences and make adjustments, but you'll be able to figure out your way through the problem. And that's really what, again, not just, not these homeworks in the end, they're there for you to practice. But what this is about is getting you to understand and use mathematics as a tool. And that's where I want to get you guys. And actually, so to do that, I very intentionally cannot teach you. If I teach you every problem that you're going to do, you're going to stay at a low level of mathematics, because you will only be able to do what you've seen. If I teach you concepts, the ideas behind them, and how to think through these problems and use math as a tool, then you'll be able to do exponentially more problems than you've ever seen. Because ultimately, all these problems that we're going to come across, they generally fit into these certain strategies and types. And so that's really what I'm teaching you guys. Anyways, so notice that it's working. We can do this problem, even though we didn't see one with cosecant and cotangent yesterday. So I am going to factor off basically a negative cosecant squared out of all this. So it'll be 3125. The negative cosecant squared I'm going to bring to the right with the d theta. So Factoring out the cosecant squared though leaves me with cosecant squared there. So cosecant squared theta. Tangent squared theta will have a negative secant squared theta with a d theta. I'll just put that on there. D theta there. So there's my du. Now, like we saw yesterday, so what I've done is now I can substitute for u here and that's my du, but we have this annoying extra piece kind of in the middle here, cosecant squared. So like we did yesterday for quite a few problems, your next thought is, well, can I turn this cosecant squared, can I turn cosecant into cotangent? Which you guys saw we actually can. Move this. Yeah, you guys saw that you actually can turn it. So how do we turn cosecant squared into cotangent squared? Using your Pythagorean identity. So cosecant squared, Pythagorean identity says cosecant squared is 1, we just did it, is cotangent squared minus 1. Or no, is it the other way around? Sorry, sorry, cosecant squared is 1 plus cotangent squared. So this is 3125 times 1 plus cotangent squared theta times cotangent squared theta times our part here that's going to end up being du. And now you can replace your cotangent thetas with u's and this with du, and you can get an integral that you can actually work out here. So what I'd like you guys to do is, I'd like you guys to work out the rest of this integral and basically, just work out the rest of this integral. You do your substitution and work out the integral. When you get that answer, though, it's going to be in terms of theta. So then I want you to explore doing your final substitution here. Just replugging things in for theta and kind of looking at what we get. Sorry. Anyway, so I won't try to lead you guys so much. So let's try to work out this integral. So pause on your side, I'll pause on my side. All right, let's see what you guys are getting. So you multiply this cotangent squared through, that's going to be 3125 times cotangent squared theta plus cotangent to the 4th theta times all this. Oh, I keep wanting to put this. And then you replace things with u's. This is u squared plus u to the 4th. Oh, man. U. And then you integrate this, and then I'll replace my u's with cotangent thetas on the next step. So integrating this is going to be 3125 times 1/3 cotangent theta cubed. Then plus 1/5 cotangent to the 5th theta plus c. All right. And we feel like we're there, but we're not quite there. So, I mean, you did your integral. So I will say, in terms of just looking back at the problem, sort of meta-analyzing where you are in the problem, what you're doing. We have done the integral. However, notice that to get there, so we had to do one set of substitutions, the trig substitutions. sort of reformulate this. But then to do this, we had to do another set of substitutions, a U substitution, to get that integral. So where we are right now is we've taken the integral, but my answer is in terms of theta, not in terms of x. So we need to get this back to x. Now, in the last problem, we ended up, so if you look back at number 3 here, we ended up with theta plus c, and theta, according to our trig substitution, was the inverse sine of x over 4. So you might think on this problem, okay, easy enough. Now I'm going to go replace theta with cosecant inverse of x over 5. However, if you do that, notice if you do that, you're going to have this sort of weird cotangent cubed of cosecant inverse, right? And it's not that that wouldn't be mathematically incorrect, but we can actually have a much simpler version of the answer if we don't go to the inverse cosecant this time. So again, it's tempting to just plug that in for theta. But notice that, so last time we just had a theta. This time we have cotangent cube theta, cotangent to the 5th theta. We have a trig ratio of theta. So what I'm saying is if you go back to your right triangle, you can actually just write in what cotangent theta is according to this right triangle written. So at the end, yes, we have thetas instead of x's, but basically what I'm saying is I'm going to replace cotangent theta with what my trusty right triangle says cotangent theta would have to be. Because if you notice, so let's go back to this triangle. So if I do cotangent of theta from this triangle, how would that read? So remember, cotangent of theta is what? Adjacent over opposite, cosine over sine, adjacent over opposite. The adjacent side from that theta is this, the opposite is 5. So cotangent of theta would be the square root of x squared minus 25 over 5. And if you're thinking this looks horribly complicated, I agree. However, notice that it allows us to replace not just theta, it allows us to replace cotangent theta with something that that at least is not only a function of x, but it's it's a square root function. And it's a polynomial, it's a rational function. It is some polynomial rational square root function of x that ultimately is a lot less complicated than thinking about cotangent of cosecant inverse, right? So it actually ends up being simpler to replace cotangent theta with this, because then I can do algebra from there and kind of simplify things and end up with relatively a much simpler algebraic expression for my answer. So that's what we're going to do. I have to turn that camera more, but we are going to replace cotangent theta everywhere I see it, this. So let me turn that camera. And then we are going to be asked to do some more algebraic simplification. But we will get to our answer. So everywhere I see cotangent theta, I'm going to be replaced with this. So we're seeing this in this problem, which again, like I said, we didn't see in problem 3. And it's just because problem 3, well, again, once we got to the end of problem 3, we just had a theta. We didn't have cotangent, cosine. We didn't have anything else there. So our only choice was to use the inverse trig function. But if you do have cotangent, cosecant, sine, cosine, whatever, one of your trig ratios, once you've built this right triangle now defines all those trig ratios, but in terms of x's and numbers and square roots, defines it algebraically instead of using trig ratios. And ultimately those are simpler, roughly, overall. Anyway, so you are going to see this in several of the problems that you do, that once you get here, if you have a trig ratio, you actually want to replace it with that trig ratio built from the triangle so that you can get an algebraic expression in the end. That's simpler. So you are going to have to kind of do this for some of the problems. Your tell is, again, that you have trig ratios here rather than just theta itself. But anyways, okay. I'm saying a lot. I'm saying the same thing over and over again. So I'm gonna also distribute this 3125 while we're at it. So this first part is 3125 over 3. And that's gonna be times square root of x squared minus 25 over 5 cubed. And then it's gonna be 3125 over 5 times that same thing, square root of x squared minus 25 over 5, but now to the 5th power, all plus c. And then we're going to go about some simplifying here. Let's see. By the way, this 3125, at some point we did the calculation for this along in the problem. But at some point, let's see, 3125, 5 to the third was 125, to the fourth was 625. This was 5 to the 5th power. You don't have to write this in. I'm going to remind myself that it's 5 to the 5th power because it'll help me do some of the simplifying here. It's 5 to the 5th power, and when I cube this, I'm going to get 5 to the 3rd power. So what that's going to leave me with is 5 squared. So this is going to leave me with 25 square root of x squared minus 25 cubed over 3. That part simplifies to that. Now, if you notice here, again, 3125 is 5 to the 5th power, and the bottom of this is going to end up as 5 to the 5th power, so those just cancel. This one is just going to end up as square root of x squared minus 25 to the 5th power all over 5 plus c. And that is our answer. That is a long problem. You ended up doing 2 different substitutions. You led off with the trig substitution, but you needed another one to kind of deal with this integral. And you even had to do a weird, just ending substitution to get back to x. That kind of is the thing with these problems. So I'm not saying it's every one of them, but yeah, they are kind of like this. Good stuff. All right. Let's see. Let's maybe look at one more. Let me erase the first panel, and I'll kind of turn the camera back over there. Actually, curious. I'll put this up. Um, Actually, to be honest, guys, I think that's probably good enough. Not only so I have time to get to, gotta try to do 3 lectures today, 3 videos today. Not necessarily just for y'all, I need to do 1 for each of my other classes, but also, yeah, the other problems are, they really, like I said, they really honestly are just the same play. And some of them are gonna be shorter, some of them are gonna involve quite a few substitutions like this. But all of them, as long as you build the correct right triangle from there, then you can work all your substitution. You can figure out your substitution and work it from there. So, okay, all right. So that'll be good enough. That'll be good enough for today. And I will see you guys for the next lecture.